Complex 1 catalyzes a hydrogen ion from NADH from the citric acid cycle to FMN, from which 2 electrons pass through a series of iron-sulfur centers to the iron-sulfur center N2 in the matrix arm of the complex. Electron transfer from N2 to ubiquinone on the membrane arm forms ubiquinol. This diffuses into the lipid bilayer. This electron transfer also drives the expansion of 4 protons per pair of electrons. Complex 2 has 2 transmembrane subunits, subunit C and subunit D, as well as the cytoplasmic extension subunits A and B. Behind the FAD unit in subunit A is a binding site for succinate, which we get from the citric acid cycle. Subunit B has iron-sulfur centers. Ubiquinone is bound to subunit B, and heme B is sandwiched between subunit C and D. Electrons move from succinate from FAD, then through 3 iron-sulfur centers to ubiquinone. Heme B acts as a shield to accept any stray electrons and catch them before they react with reactive oxygen. Ubiquinol from complexes 1 and 2 passes 1 electron through an iron-sulfur protein, which passes it to cychrome C1 and finally onto cychrome C, while also moving 2 protons to the intermembrane space. The other electron for ubiquinol cycles through cychrome B, bringing 2 more protons to the complex. It then follows the steps of the first electron, moving a total of 4 protons to the intermembrane space and reducing 2 cychrome Cs, which move to complex 4. This happens from each ubiquinol that comes to complex 3. Cychrome C transports a single electron via a heme group within the protein to cychrome oxidase, also known as complex 4. The electrons flow from cychrome C to copper A, which consists of 2 copper ions. They go on to heme A and heme A sub 3, and copper B. Copper B is a copper ion bound to heme A sub 3, which transfers the electrons to oxygen, the final electron acceptor. 4 electrons reduce a single oxygen molecule into 2 water molecules. Meanwhile, 4 protons are moved from the matrix into the intermembrane space. Chemiosmotic theory uses the flow of protons down their electrochemical gradient to counteract the unfavorable thermodynamics of ADP phosphorylation. To establish an electrochemical gradient, the electron transfer chain couples a downhill flow of electrons with the uphill flow of protons. It is this gradient of protons that is used by ATP synthase to phosphorylate ADP. A proton then enters the F0 complex through the IMS half channel, where it binds to an asparagine residue. This displaces a positive charge on the arginine 210 residue, which then rotates and displaces the hydrogen. The C10 ring rotates and the arginine 210 returns to the P side half channel. Rotation of C10 moves the gamma subunit, which changes the conformation of the alpha and beta subunits. The beta ADP site is converted to the beta ATP conformation, which promotes the condensation of bound ADP and inorganic phosphate to form ATP. The ATP conformation is converted into the beta empty site, and the beta empty site becomes the beta ADP site, which loosely binds ADP and inorganic phosphate from the solvent. Through one rotation of the gamma subunit, each of the 3 beta subunits will go through all of the 3 conformations. And here is the process uninterrupted.